There we go. Okay, now we're live on the internet. All right, so optimization problems. We're going to try to solve a few. We'll get like 20, 25 minutes, and I got to start a new topic. Baseball team plays in a stadium that holds 66,000 spectators with a ticket price of $12. The average attendance has been 27,000. When the price dropped to $11, the average attendance rose to 33,000. Assume that attendance is linearly related to the ticket price. And apparently I forgot to copy the question. We're probably trying to maximize revenue.
What ticket price is maximized?
Yes, okay. So first we have to find the supply and demand equation for the price. So I'm going to make a quick table here, and we have price, and then let's see, we have attendance. Let's call attendance X. So when the price was $12, attendance was 27,000?
Yes.
And when the price was 11, attendance was 33,000.
Yes.
Okay, and I probably should have switched those. Let's see. See what happens. I want an equation with the price. Yeah, I should have switched those columns. Oh well. So the price is going to be my y. So my change in y here is what? 2? No, 1.
1.
I knew that. So change in y, we're dropping by 1. And the change in x is 6,000?
Yeah, 6,000.
We have an increase of 6,000. Okay. And if we just pick one of the points, then let's see, I'm letting p be my y. So I would have p minus, I don't know, I like 33,000 better. It's a cute number. Would be equal to negative 1/6000th times x minus 11.
Does it matter which one you use for x?
Doesn't matter.
Wait, what?
Because I think the video might have used
The video put
the
your
price for x.
price for
Does it say?
Did he find M?
Don't worry about it. Just,
Okay.
this is going somewhere. Sure.
Just roll with it.
Let's roll it.
How did we
Okay.
find M?
You do the
It's
slope.
rise over rust.
So, okay.
So, so here I'm letting p be my y value. I just put the columns in the wrong order initially.
Thank you.
Yeah, so change in y is if we drop the price $1, attendance goes up 6,000. So that's my slope here. So this is, again, change in price over change in attendance. So that means my equation for the price is going to be, cleaning that up a little bit, negative 1 over 6,000 times x plus 11 over 6,000 plus 33,000 when I bring everything to one side. And do I have to clean that up?
Yeah. I mean,
you have two constants.
Yeah, that's okay. We're just going to go with that.
Okay.
All right, so that's the price. Revenue is price times quantity. So if I just multiply that by x, then I have my revenue equation. Okay. So new page. So revenue is then going to be equal to negative 1 over 6,000 times x squared plus 11 over 6,000 times x plus 33,000 times x. That's my revenue equation, price times quantity. So just a reminder, I just took the price equation multiplied by x. Price of the ticket times the number of people that bought tickets. And now we want to see what happens to that function in terms of a critical value. So that means we need to find the r, the x. So first term, we're going to get 2 times negative 1 over 6,000, which would be negative 1 over 3,000 x. And then Derivative of the next part is just 11 over 6,000 and 33,000.
Now can we combine the constants?
I don't really care about an exact answer, so you could, but I'm not going to. I'm just going to set it equal to 0 and solve.
Multiply it.
So then to solve this, I'm going to bring the constants over to the other side.
Okay.
Right, so I'm going to have a negative 11 over 6,000 minus 33,000. And then I'm going to multiply by the reciprocal of negative 1 over 3,000, which is what?
3,000.
Negative 3,000, yep. So then we multiply that by negative 3,000. And that should be the x value that I want. And I'm just going to plug that into a calculator because I don't really care about the exact value. I can see it's going to be a positive number. Oops, that's not the calculator. Where's my calculator? Different screen. There we go. All right, so I want 3,000 times.
You want negative 3,000.
I know, I'm just going to get rid of all the negatives.
Okay.
Divided by, no, let's see, what's next? 11 over 6,000 plus 33, 1, 2, 3. So you can use negatives if you want. Ooh, shit, I got a mistake somewhere.
That is way too much.
That is too much for the attendance. Okay. So where did I screw this up?
Look it back.
Let's see.
Just have the bracelet.
No, this is X. This is the number of attendees, but that's not possible because there's only 66,000 people. Okay, so.
Start from the beginning.
Maybe make X 66,000 maybe. I don't know.
Okay, so this page looks okay.
Wait.
What's up?
So to move negative 1 over 3,000 x, you plus it, and then wouldn't you divide by?
That's the same.
Dividing by 1 over is multiplying by 3,000.
But then why is the negative still there?
Well, they cancel out, so it doesn't matter.
Yeah, negative times a negative is a positive. So this part's right, this part's right. So that means there's got to be something wrong with my revenue equation. So let's back up and take a look at that.
Did you solve for 66? It's a linear equation, so shouldn't you solve for the start?
Well, here's my linear equation right here. So I have slope and y-intercept.
And then you multiply it by x.
So revenue is nonlinear.
Yeah.
Which is
For
definitely
my-
true.
My revenue equation, I did X times Q of P.
But I get you. I think so.
So I took
X.
your P right there.
Mhm.
I just timed that by X.
Yep.
And then, so,
That's revenue.
yeah, and then that's your revenue equation. Then I
Right.
set the, then I got the,
Oops.
shoot. I did it different than you.
Yeah.
Instead of doing the bigger numbers for X, I did them for Y. Actually, I did them for X instead of Y.
Okay, so I'm just going to start over and see what happens.
I got 15.5.
Don't multiply by
For that number?
No.
That can't be right.
For ticket price, I got $8.25.
That's what I
Okay.
did it.
I don't know. Because you have to find.
Basically,
I think your first one's right.
All right, I'm just going to start over. Oops. All right, one more time. So let's see. So for the equation, I'll try reading it the other way. So let's see, if I put x here and p there.
Well, you have to solve it for the maximum stadium spectators. So for the last one, instead of
Well,
just set it equal to 66,000 again. Would that be it?
I don't think the 66,000 really comes into play at all. That's
Yeah,
just
I
setting it so you know that
yeah, I
you
don't
can't
think
go
that's
above.
the limit.
that's
Okay.
relevant. So for sure, we know that if the ticket price is 12, then we'll get 27,000 people attending. And if the ticket price is 11, we'll get 33,000.
So you find the slope, right?
So you have the same slope, right, Carter?
No.
No. You did it upside down from that?
Yeah, so my slope is negative 6,000.
Yeah, because every time you
Yeah.
increase the price, less people come, right?
Yeah,
So you had your table back the way I had it here?
It should be on like
So
this.
it's-
No, he had it backwards.
Yeah, I had it. Oh, no, yeah, is it?
No, he had it the way you just set it up.
Can we just do X and Y?
Because
That's
that
the
would
same way.
put,
Yeah, that's the same thing that you had on the other side.
yeah, you
Yeah.
have to make, you
just
have to
wrote
make the
table
price
backwards
X and the
We use the small numbers
attendees
for
Y.
X and the.
No, I did the attendees X and the
Yeah.
price Y.
I
Like
think
this right here?
Yes.
Okay.
Oh,
So, but the problem with this right here is my change in Y is -1,
Yeah,
and my
Like a
change
flip
in X is 6,000.
so you
So
still
the
end up
slope,
with
if
the
you do
same.
it this way, is still -1 over 6,000.
So your attendees do have to do Y and your
So
price
you were
has to be
doing it
X.
Backwards
Oh,
from
Wouldn't it
that?
just
maybe
make more
backwards.
sense to make the price,
So this
Price
is
should be X.
change in
Price is
price.
or no, price is independent.
price is independent to the.
This is change in price over change in people, change in attendance.
I don't understand why it's over.
But isn't
Extra
the
L.
change
Oh, yeah,
in
you're right,
people
yeah.
dependent on
Like,
the change?
Yeah,
I did
in-
price,
attendance
price
Y.
should be an independent variable.
No, it
This
says
situation.
assume that attendance is linearly related to ticket price. That means that as your price goes up or down, your attendance also goes up or down.
So price is
All right, so he's doing it backwards then. Okay, so let's think about it that way just
Oh,
for a minute.
no.
So suppose we flip this to go back to the way it was. All right, so we're gonna try this one more time. Eventually. It's good to have, this is what it's like to solve a math problem you haven't solved before.
So it's P and Y?
Yeah,
So we're gonna go the other way. So we're gonna,
1,000 over
No, that's
-1.
not.
yes.
yeah, we can do it this
Yeah.
way. So I'm gonna call them X and Y,
Okay.
and
Price should be
X is going to be price, and Y is gonna be people.
Okay,
Whew.
I gotta do this again.
So then I go from 12 to 11 and 27,000
Oh, I was doing it right
to 33,000. It should have worked the other way too. I'm kind of curious about why it didn't. I'll have to come back on that. So then here, we're gonna have a slope that's change in people over change in price.
now. Okay, I did that.
And that's going to be 6,000 over -1. So we call that negative 6,000.
But
Yeah.
that's.
So then to generate an equation for this, calling that Y, which is people, I could do Y minus 11 is equal to negative 6,000 times X minus 33,000.
Or you can solve, yeah, that works.
So then I'm gonna get Y equals negative 6,000 X plus 33,000 plus 11.
That looks a little bit funky.
So now I
Y
have,
plus
No, it should-
33,000.
Yeah, it should be Y plus.
oh shit, I forgot to multiply. Damn
Did you on the first one?
it.
I don't think you did. I think
No.
that's what you missed on the first one.
You think I missed a multiple? Oh shit,
Yeah.
I did. Oh yeah, Sarah found the error.
Yeah!
Yeah, I gotta
See, this is
distribute
why you
here.
combine my terms, Gary.
Thanks, Sarah. So let's see, 6 times 3 is
Wait,
what?
wait.
Like this.
What?
Shouldn't it be Y
18.
minus 33,000 and then X minus 11?
Oh shit, I got those guys wrong.
What
Ah.
are you doing? Right.
This is like the struggle I went through the entire time I worked on any of these questions.
See,
This
maybe
does not go
maybe
well.
this isn't,
I'm
maybe
glad
this
I'm
isn't necessary.
into-
Was the assignment really necessary?
Yes. Even if I get them wrong once in a while, which I told you, a lot of times, the first time I try these, I get it wrong the first time. This is the first time I tried this wrong. All right, so trying yet again, Y equals negative 6,000.
X.
Plus, X,
X.
plus 66,000
Yeah.
Yeah.
plus 33,000.
So you get 99,000.
So I get negative 6,000 X
Plus 90.
plus 99, 1, 2, 3. All right, so here, this is the equation for the number of people.
Yeah.
X is the price, so this is quantity. So we're gonna multiply this by X.
Yes.
For the revenue.
All right. So now we have revenue is equal to -6,000 X squared plus 99,000 X.
And you set that to 0.
And we set that to 0.
No, you found the
we gotta
derivative.
take the derivative. Hang on, Beatrice. Screw with me up. Green.
That's why.
Wait a minute, I'm already screwed up. Okay.
Wait, no, I did take the derivative. What?
All right. It's gonna be -12,000 X plus 99, 1, 2, 3.
Confusion.
Then you set it to 0.
Now we set it to 0. So then we get X is 99,000 divided by 12,000. Signs work out nice.
Which is 8.2.
X.
So that's like 99 over 12, which is approximately what?
8.25.
8.25.
All this
I think that's exactly 8.25.
Exactly 8.25. Could be. Let's see, the 3's divide out, so that would be 33 over 4. And yeah, 4 goes in there 8.25 times. Yeah.
What am I doing wrong?
That is correct.
So,
All right.
Did you get the
okay.
exact
Can we
same
plug it
answer?
in to make sure we did it right?
What's that?
Can we plug it into math?
Although
Not
it's
yet.
like
I
weird
think
words.
I found the error.
Yeah, because -11.
Like I see.
Let's see, Oh, I put these numbers in the wrong spot.
And it still worked out?
No, the first one did.
Oh.
Yeah, that was the first.
I did that both times. I put the numbers in the wrong spot. This should be if price is 11, people is 33,000. So this way would have worked too had I not screwed that up.
I think you did it first time.
Just cross that.
Yeah. Okay, so that is screwed up there.
Okay.
All right, so that method would have worked had I not screwed that up. Okay, so. Yeah, so I'm gonna solve it that way now to check.
Oh wait, you're gonna do it the other way now?
I'm gonna do it the other way, make sure I get the same answer.
Yeah.
So, let's see. So I'm gonna get P equals -1 over 6,000 X. And then, let's see, I had these numbers backwards, so that should have been 33,000. So then I'm gonna get plus 33,000 over 6,000.
Oh, yeah.
And then this should have been minus 11. So then I'm gonna have a plus 11 there. That's the way it should have looked for the price. So let's see, cleaning this mess up. Zeros cancel, 6 goes into 33, what? That would be 11 over 2, which 11 over 2 is 5.5.
Yes.
Okay, so I have then price is -1 over 6,000 X plus 16.5.
Yes.
They're looking better. So then revenue, choose blue for revenue, would be -1 over 6,000 X squared plus 16.5 X. The RDT.
Nope. DX.
X, yeah, there we go, is equal to -1 over 3,000 X plus 16.5.
16%
Equal
Set
to
to
zero.
So
zero.
that's sucker equal to 0. And then I get X is equal to 16.5 times 3,000.
Which would give you the amount of people in the
Which should give me the
audience,
optimal number of people.
right?
What did we want to answer here anyway? We want the optimal
Right.
revenue?
Money.
Let's see. We want,
Cash monies.
what ticket price would maximize revenue? Yeah, so doing it the other way takes you straight to that ticket price. So here now I have to plug that answer into the ticket price equation. So that's going to give me -1 over 6, 1, 2, 3 times, we got what, 3,000 times 16.5 for the optimal attendance. And then
Plus
what?
16.5.
Plus 16.5. Gives us 8.25. Woo! We
I
worked.
think the other way sounds way easier.
Well, how do you know what's the easier way until you do it both ways?
That took us 25 minutes to do.
Look at it, wait, Daphne.
Divided by X. And say it took an
Okay, good question. So Dylan asked, why did I know to multiply by X right here? And so the piece of information, and that's always true with these problems, you gotta find the right equation. So revenue is just how much money you take in. And the simple version of revenue is just take whatever the price is and multiply by however many you sold, quantity, price times quantity. And that'll give you the revenue. So that's the way that works there. Okay, wow, that was exciting.
Cool, so there goes all our 25.
Yeah.
Yeah.
All right, let's do another one. Let's see, we want to vote 6, 8.
Haven't done that.
All right, let's see, what's 6? 6 is the cylinder. Okay, we did one like that in class last week.
6 gives you all the stuff you need to
Yeah.
answer.
Okay.
Yeah, we're doing 6. No.
6,
That's dumb.
No.
7, the rancher fence, that's not that bad.
No one gives you all the stuff you need.
8, the Norman window. You got to look up what a Norman window is. What's a Norman window?
It's a
That's a
rectangle.
one.
It's got a semicircle on top. That's all a Norman window is. Okay,
Rich people.
rich people windows. Yeah.
Has rectangles.
9's not too bad. Fence, that's not bad. That's kind of like 7.
And we did
Oh, yeah.
class, right?
And we did this one in class the other day. Yep. All right, so I'm gonna let you guys struggle another day with these. Anybody want the homework open for one more day?
Yes, please.
Okay, let's do that then.
Oh, gosh.
Y'all ready for 4.8?
And now we're gonna do 4.8.
Is that L'Hôpital?
L'Hôpital,
It's
yes.
The hospital.
Is
The
that,
hospital.
French, the
but
hospital.
is that easier than our regular derivative method, or is it much?
You'll see.
Hospitalized.
Yeah,
Can you just-
hospitalized,
Okay,
that's
so I'm gonna
why
make this
it's
do the
called
28th for everybody.
Thank you. Sweet Jesus.
Okay.
Bless your soul, Mary. Bless your soul.
Wow, Christmas miracles are real.
And this next section's pretty easy.
Gary, this is your Christmas present to us.
An
All
extra
right.
day on our homework?
So 4.8 is about two things. L'Hôpital's,
Wait, where's the act? Where's the?
there's
is
no
it over the-
S.
No, isn't it? No, over the O. There's like the.
Oh, it's an umlaut?
Thingy.
Yeah, it's the chapeau. It
It
means
means
hat. It means
Hat.
hat. I took French for like 3 years.
Sombrero.
It's finally actually being useful.
So L'Hôpital's rules for limits. Along with this, we're gonna do another topic called indeterminate forms. Indeterminate forms. And I've talked about this a little bit a long time ago in class, so I just want to remind you about
How long
this.
ago?
Probably week 1.
Yeah, no.
So an indeterminate form is some expression that we look at and we're like, I don't know what the answer is. I can't determine the answer. Indeterminate, right?
Oh, it does not exist.
No, it's not does not exist. It's just that cannot be determined at the moment. So for example, consider 0 divided by 0. What does that equal? Well, that is a lot like 6 divided by 2. What does 6 divided by 2 equal?
3.
3. Why? Because 3 times 2 equals 6, right? If you go around in that direction as multiplication, that's why. That's one reason. So here, if I follow that same reason, this means question mark times the bottom 0 has to equal the top 0. Anything can work, yeah. So anytime you end up with a 0 over 0 in a limit, what that means is, I don't know yet. It could be anything. It could be 4, it could be 5, it could be pi, it could be 0, it could be infinity, or it could not exist. It could be 5. It could be 5, yeah. So we played around with this in week 1, so we're coming back to it with a new technique. The new technique that L'Hôpital came up with was he noticed that when you're taking the limit of a quotient, let's say f of x divided by g of x, that limit happens to be equal to the limit as x goes to a of f prime of x divided by g prime of x. That the limit of the quotient of two functions is equal to their derivatives if, and this is a huge if, both the limit of f of x and the limit of g of x are 0.
That's
Both of them have to go to 0. This has got to be a 0 over 0 situation. Okay. If it's not 0 over 0, L'Hopital's rule does not apply. Well, if it's not 0 over 0, then maybe it's something like 0 over 2. What's 0 divided by 2?
0.
That's 0. Maybe it could be 2 over 0. What's 2 over 0?
Undetermined.
Indeterminate. No, that's undefined, actually. And undefined could be really undefined, or it could be negative infinity or positive infinity. Right? So if it's not 0 over 0, we have other ways to deal with that. That's not a big deal. L'Hopital noticed that if it is 0, 0 over 0 is a problem, and he noticed that the slope functions, they have the same quotient in the limit as the original function. Okay? And if you think about it, graphically, it's pretty darn obvious. So suppose that this blue function here is f of x, and this red function is g of x, and that's the value a, right? They both go to 0 at a. Okay? Well, if you look at the slopes of each of these, aren't they, if you zoom in, they're going to be kind of indistinguishable from the actual functions. That's the idea, because the derivative is the slope function. So that's where it comes from. So there is a proof of it. The proof just involves the limit definition of the derivative. I'm not going to do it. We're just going to apply L'Hopital's rule. So let's apply L'Hopital's rule to a couple functions we know, and then we'll go to try and apply it to some functions we don't know yet. So consider the limit as x goes to 5 of x squared minus 5 over x minus 5. We dealt with this this is a 0 over 0. Everyone agree?
Yep.
Yes.
Yeah. We dealt with this algebraically before. We're just going to try L'Hopital's rule and see what it says. So L'Hopital says, hey, you can take the derivative. Now, this isn't the quotient rule, right? I'm taking the limit at the top separate from the limit at the bottom. What's the limit of the numerator? I mean, sorry, the derivative of the numerator.
2x minus.
It's just 2x, right?
Yeah.
And what's the derivative of the denominator?
1.
1. So now L'Hopital's rule, so I'm going to put a little L there to indicate L'Hopital's rule says they're equal. Because otherwise I'd look at that and say, what weird algebra did you do, right? And this is L'Hopital's rule. We apply derivative of the top, derivative of the bottom. Now what happens if you cheat and try to plug in 5?
10.
You get 10 over 1 or just 10, right? Compare that to the algebra we did before. X squared minus 5 factors as x minus 5 times x plus 5. The x minus 5 say, hey, together, as a quotient, we're really 1. Leaving the x plus 5, and when you plug in the 5, this goes to 10 as x goes to 5. Right? That's the way we did it algebraically back in like week 1. So L'Hopital's rule is just a different way to approach these 0 over 0 limits.
Can we use
Carter?
Wait, how does x squared minus 5 factor into x minus 5?
Oh shit.
That's what I was saying. I was like,
Sorry.
what?
This was supposed to be a 25. Okay.
Cool.
Oh, okay.
That
That
makes sense. I'm like, what?
Oops.
I was like, it's not 0 over 0.
Okay. Yeah, so now this is 0 over 0. Now this factors.
No.
And now it works.
No, no.
All right. So another one that we've done before. Limit as x goes to 0 of the sine of x over x. Now we had this wild and crazy trig proof of this. It was very complicated. It took like 4 of these magical whiteboards to
Doesn't it just
do.
equal that?
So this is a 0 over 0, right? What did we determine the derivative, the limit was way back? In like, this was week 2, I think.
One
We determined the limit was 1.
is
Yeah.
one.
Okay, and we had this wild trig proof of y, right? We had to break out the unit circle, do a bunch of identities. So let's apply L'Hopital's rule. So if I apply L'Hopital's rule, derivative of the top is what?
Cosine of x.
And the derivative of the bottom is
1.
1. And cosine of 0 is
1.
1.
So when we can change like numbers in, right? Because it's 0, we can do this.
Yeah. Yeah, so this is what's called an indeterminate form, because when I try to cheat, I get 0 over 0, which is indeterminate. Means I don't know enough yet. I got to do more work to figure out if it does become something. Right? And sometimes it's going to be 10. Sometimes it's going to be 1. Sometimes it's going to be infinity. Sometimes it's going to be 0. Sometimes it's going to be 5. Okay? Other indeterminate forms. Are infinity over infinity. Sometimes that evaluates out to be something. Oh, let's see, there's a whole bunch. I made a list. 1 to the infinity. That may not be 1.
One to the infinity.
No. 0 to the 0.
That's one, isn't it?
Not necessarily. So here's the problem with 0 to the 0.
Anything.
If you have 0 as the base,
Oh, anything to the 0.
0, what's 0 to the second?
0.
What's 0 to the first?
0.
So according to that rule, 0 to the 0 should be 0. However, what's 2 to the 0?
One.
What's 1 to the 0?
1.
So what should 0 to 0 be?
One.
Oh shit, which is it, 0 or 1? I don't know, those are both good rules, right? So that's an indeterminate form. You don't know until you do more work. Okay. 0 times infinity is indeterminate. Infinity minus infinity. There are others, but those are the main ones we come across with like everyday kind of functions. So depending on the limits each of these things came from, they could come out to be some real number. What's up?
Why 0 times infinity?
Isn't anything?
Because like anything times 0 is just 0.
So 0 is like infinitely small. Infinity is infinitely big. What happens when infinitely small and infinitely big do battle? Could one cancel the other? Turns out sometimes they do.
Really?
Yes, I'll give you an example. So suppose I wanted to do the limit as x goes to 0 of x times the natural log of x.
If it's 0.
So what is x doing? It's going to 0. So this looks like it's going to be 0 times, what does natural log of do as x goes to 0? Think of the natural log function. It doesn't go straight up, it goes straight down. Yeah, so this is 0 times negative infinity. So who wins here? X getting smaller or natural log getting bigger? Let's see. So this is not L'Hopital's rule. However, check this out. Multiplying by x is the same as dividing by 1 over x. Right? Because you can go the other way. Dividing by 1 over x is the same as multiplying by x. So this thing right here is algebraically equal to that thing right there. Okay, so now let's go take our limit. As x goes to 0, and this becomes, let's see, as x goes to 0 on the top, I get a negative infinity. And in the bottom, I get an infinity. And it turns out L'Hopital's rule applies to either 0 over 0 or infinity over infinity.
Oh, no.
So we're going to apply L'Hopital's rule to this. So, according to L'Hopital's rule, what's the derivative of the natural log of x?
1 over x.
This is 1 over x, so that's my new numerator. What's the derivative of 1 over x?
Negative 1 over 2x, or x squared.
Negative 1 over x squared. So L'Hopital's rule says this top quotient has the same limit as this new quotient here, as x goes to 0. Now this cleans up quite nicely, because this becomes 0. 1 over x times negative x squared over 1. And that cancels quite nicely. To what?
1 negative.
Negative x.
Negative x. So this algebraically then becomes the limit as x goes to 0 of negative x, which is?
Zero.
Which is 0. So who won the battle up here between 0 and infinity?
0.
0 won that battle. Does 0 always win?
No.
It depends on the functions. Depends on the functions.
Okay.
Isn't this exciting?
So much fun. No, I like thinking about that.
I don't
All right,
This is
Fist fight.
interesting.
let's try another one. How about should I do a known or an unknown?
Unknown.
Unknown, okay. Limit as x goes to, not that, wrong one. X goes to, ooh, this is a hard one. 1 of x over x minus 1 minus 1 over the natural log of x. At first glance, what happens here? If I plug in 1 to the first thing, I get 1 over 0. Okay, so I got to adjust, let's see. Yeah, 1 over 0, problem. If I approach from, let's see, the right side, then I get 1 over 0 becomes infinity, positive infinity. On the other side, it would be negative infinity on the other side? Yeah, it would be negative infinity on the other side. And then what's natural log of 1?
1.
1, so it's 1? Negative 1?
No.
Wait, oh,
X
natural
one.
log.
So that'll be x to the first equals. No.
Oh, rough day in paradise here. It's 0. Natural log of 1 is 0. So this becomes 1 over 0. If I'm on the positive, the right side of 1, then it's a positive 0, not a negative 0. And so I get 1 over infinity. So this right here is infinity minus infinity. What is infinity minus infinity? Is it 0? Is it something else?
No, dear.
It's two different infinities. Then it would be 0.
Different infinities is a whole nother weird subject. Well, it is. I mean, think about it. Just with whole numbers, how many whole numbers are there?
Infinite.
Okay, how many even numbers are there?
Infinite.
But there's half as many even whole numbers as there are whole numbers.
Because one
Oh,
infinity is
no.
bigger
Right?
than the
So
other.
infinity is just a weird topic. So I got a problem here. L'Hopital's rule doesn't apply at the moment, so I'm going to do some algebra to this. And I think Sarah would very much like it if I added these fractions together.
I would
Okay.
appreciate it.
So
Thank
my
you.
new common denominator is going to be x minus 1 times the natural log of x. Numerators are going to be x times the natural log of x. So this would be a natural log minus x minus 1. I'm going to ignore the limit for a minute while I clean this up. So let's see, does that clean up much? Not really.
Get rid of your natural law.
No, nothing
You
cancels
can just
here.
you can just change the signs on the.
Yeah, I could. So I could write it as net x natural log of x minus x plus 1. Do I want to distribute the natural log? I think it benefits me to not distribute. I'm going to leave it as x minus 1 times the natural log of x. All right, now what happens if I try to take the limit again as x goes to 1 from the positive side?
We still get 0 on the bottom.
I get 0 on the bottom. What do I get on the top?
0.
I get 0 on the top too.
Yeah.
Yeah. So this is now 0 over 0, so L'Hopital's rule applies. So I've rewritten infinity minus infinity as 0 over 0. Does that always happen? The answer is no, it doesn't always happen. You got to check every time. All right, but I'm in a position where I can take the derivative of the numerator and I can take the derivative of the denominator.
Oh, goodness.
Yeah, right. So take the derivative of the numerator, which involves the product rule for part of it. And the product rule again down here. All right. Good luck. So according to L'Hopital's rule, what is this going to be equal to?
So there's an x over x, which is just 1.
Minus 1. Oh, shit, yeah, plus.
That's what I get at first glance. And I gotta clean that up a bit.
And, oh, that's technically 1. You're right.
So let's see, this is 1 minus 1, so that's nice.
Wait, why is,
1 over.
where did the minus come from?
Where, what minus?
On the top?
This one right here?
Yeah.
The derivative of
The
negative
derivative
x
of negative
is
x.
-1.
The one happened, oh yeah, the plus 1. Okay, that
Derivative
goes
of
away.
1 is 0.
Yeah.
Yeah, so this becomes, I'm gonna pick a new color, the limits as x goes to 1 on the right side. So in the numerator, I just have the natural log of x. In the denominator, I get the natural log of x plus 1 minus x.
Yeah. Yeah. You still can't plug in 1
So let's see, if I try to plug in 1, I get 0 on the top
and 0 on bottom.
and 0 on the bottom.
Can we do that again?
Turns out if you have 0 over 0, you can use L'Hopital's rule again.
Can you really?
So we can just keep.
Because this is just some new set of functions. Yeah, you can use it over and over again, which is both a good and a bad thing, as I might show you in a minute.
We're just gonna keep doing this.
So,
Is it gonna keep going?
well, that's what you gotta find out. Yeah, so let's do it again. So I'm gonna copy that and move screen. So 0 over 0 is what this evaluates to, which means I can use L'Hopital's rule again. Page, move you up here. So what I'd encourage you in your notes is anytime you use L'Hopital's rule, above the equals, put an L. Because otherwise you look back and say, what bizarre algebra did I do there? Right? It doesn't make any sense. Trust me, it's happening. So let's see, derivative of the numerator is just 1 over x. The derivative of the denominator is 1 over x minus 1.
Still gets your inbox.
And multiply top and bottom by x.
Yep.
So this becomes the limit as x goes to 1 from the right side of 1 over 1 minus x.
You still get 0 on the bottom.
Yeah, I still get your bottom.
That's okay.
That's 1 over 0 though.
Yeah.
It's 1 over 0. And 1 over 0 is either plus or minus infinity, depending on what's happening. So here I'm picking 1 on the right side, right? So that means if you look at x versus this thing, I'm looking at numbers like 1.1 and then 1.01. So that means down here, 1 minus, so that's going to be 1 over negative 0.1, which is negative 10. And this is 1 over negative 0.01, which is negative 100. So as x heads to 1,
Infinity.
this is heading to negative infinity.
And that's your answer, right?
So in this case, 0 over 0 is negative infinity. Or the original version was infinity minus infinity, turned out to be negative infinity in this case.
So negative infinity 1.
So negative infinity time, or, well,
So yeah, it looks like the second infinity beat out the first one. Yeah. All right, so one more case and then we're on time for fun with this stuff.
Can you do it in 2
infinity
minutes?
times 0
Yeah,
equals 0.
consider x goes to infinity of e to the x minus e to the negative x over e to the x plus e to the negative x.
Isn't it?
What's the opposite?
No, because they're
The
being
opposite
added and
sign. Yeah,
subtracted.
the opposite signs.
So as x gets huge here, e to the x gets huge, but e to the negative x gets small, 0, right? So this becomes, the numerator becomes infinity, ooh, whoa,
Negative.
infinity, infinity minus 0, and in the bottom you have infinity plus 0, which is infinity over infinity. And L'Hopital's rule also applies to infinity over infinity. So if we apply L'Hopital's rule, then we get the derivative of the top would be e to the x minus the negative e to the negative x, or plus e to the negative x. In the bottom, I'm going to get e to the x minus e to the negative x.
But then we just flipped it and we still have infinity.
We have flipped it,
over
we have the
infinity.
same problem. And if we take the derivative again, it's going to flip it again. So this one you can apply in L'Hopital's rule infinitely many times and you're out of luck. Yeah. So L'Hopital's rule is powerful, but it doesn't always work. So
Okay.
then I go back to this and say, okay, apparently I should do some algebra. So the algebra to do on this right here is to multiply top and bottom by e to the x.
We get you.
Okay, so this is not helpful there. Limit as x goes to infinity. That gives me e to the 2x minus, what's e to the negative x times e to the x?
Even the first.
It's 0.
E to the 0, which is 1. Yeah.
Oh.
Okay. And if I try to cheat here, I get infinity minus 1 over infinity plus 1, which is infinity over infinity. Now apply L'Hopital's rule. Is 2e to the 2x over 2 e to the 2x,
It's 1.
Which is just 1.
which is 1.
This is.
So the limit is 1.
Oh my goodness.
Okay.
Because that's a.
Yeah. So L'Hopital's rule is powerful and it applies to a lot of different situations. It doesn't apply to all situations. You've got to, before you use it, you got to make the thing look like 0 over 0 or infinity over infinity. And then you can apply it. All right. So tonight and tomorrow's just funky limits. If you still have questions on those optimization problems, we can do another one tomorrow.